No.
No.
About last class's exercise.
Yeah.
What value were we supposed to find?
I don't know.
Okay. Well,
What was the exercise?
there were two factories, A and B. In one, we had like 1 on 100 washes that were defective, on the other 1/200, and we had to find the probability that the second watch is okay, knowing that the first one is.
Okay. Okay. Yeah, I remember now. I have to check on my notes. I think it's much before than that. Yeah, because this is the thing we are going to do today. So before blah blah blah. Finite random variables, expectation. So that's the thing we finished. It's with expectation. I think we finished last time.
Yes.
Where is the factory thing? Oh yeah, it's here. Okay. Yeah, we didn't finish the correction of the exercise. So if you want, we can finish. Okay. The fact is that in this case you will need to make some hypothesis on the problem. Okay, and this is a general thing you must retain and remember, is the fact that usually we have to make some hypothesis for our problem, additional hypothesis, if you want to get an answer. Okay. So I can finish the thing. Yeah, so we have a priori hypothesis. Okay, hypothesis H. That was that the probability that y equals to A can you hear me?
Yes.
Yes, we can.
I don't know why my tablet stops. Let me change. Sorry, I have to change from my. No, yeah. It's okay. Oh, what happened? Well, I don't know. Something happened. Okay, it's everything is perfect. So the probability that the watch comes from A is 1/2, and it is also the probability that the watch comes from B, the factory B. Okay, and since we assume that the states of successive watches are independent, we have that the conditional probability that says that the probability that x1 equals 1 and x2 is 0 given y equals to A. Okay, do you remember that xn is the state of the nth watch in the container, and xn equals to 1 if the watch is okay, and xn is 0 if the watch has some problem. Okay, so now I say this this probability, this conditional probability satisfies the following inequality. Sorry, this is equals to the probability that the first watch works equals to 1, given that it comes from factory A, times the probability that the second watch doesn't work, given the fact that it comes from factory A. Okay, and the problem gives us some data. We have some data, some information from the problem, which is the probability that xn is 0 given y equals a is 0.01. Okay, so what's the probability that the nth watch doesn't work given the fact that it comes from A is just the proportion of not working watches in the produced by A. Okay, so this is a data from the problem, and we have another one, which is the probability that xn is 0 given y equals b. That's the proportion of watches coming from B that do not work. This is 0.005. Okay, is it good for everyone? Now the problem asks for the following: what's the probability of x2 equal 1 given x1 equals 1? So what's the probability that the second watch I take from this amount of watches works, given the fact that the first one I took also worked? Okay, we know that this conditional probability, by the definition of the conditional probability, is equals to the probability of x2 equals 1 and x1 equals 1 divided by the probability of x1 equals 1. We divide by the event that's in the condition. Okay, x1 equals 1. Okay, that's the base formula. Now we have to say something more fine about the numerator of this fraction. Okay, we have to compute this probability, and we will use the total causes probability. Okay, so this event, maybe I can take it directly, and this probability is actually equals to a sum of probabilities. The first probability is the probability that x1 equals 1 given x1 equals 1 and x2 equals 1 given y equals a times the probability of y equals a, this is y equals a, because this has no meaning, okay, plus the probability that x1 is equal to 1 and x2 is equal to 1 given y is equals to b times the probability of y equals b. Okay, so this is the proportion of watches coming from factory A. This is the proportion of watches coming from factory B. And inside of each cases, I have some conditional probabilities. Okay, the first and the second watch I took, they are okay, given by the respectively factories. Okay. Okay. So now I have some numbers here. So this is actually just equals to 0.99 square times 0.9, sorry, 0.5 plus 0.995 square times 0.5. Okay. Now, what's this number? Well, I have to compute it because I don't have. Let me check on my computer.
Please, sir.
How many?
I don't understand why it's 0.99.
C'est une donnée du problème. C'est la proportion de montres défaillantes. It's the proportion of not working watches.
Why is square?
Hmm?
Why are you putting 0.99 square?
Why I put that square?
Yes. I was thinking that it would be 99 on 100 multiplied by 98 on 99.
Sorry, I can't hear you very well, but you don't agree with the numbers. That's your question. That's right.
Yes.
How many difference do you have with respect to me? No. Okay. Look, you have inside of A. I mean, if you consider okay, you have two populations. A. You have population A here and B. Okay. Now, you want to know what's the probability that two consecutive two consecutive samples from A. Okay, that's why it's here given A. So it's 0.99. And since you have two of them, you have this square. Is it clear? Is the square that you don't understand, or it's the number 0.99?
It's the square, because if I remove 1, the first is 0.99, the first probability, but the second is not 0.99.
Yeah, I mean, the first, how to say, maybe with colors. This square 2, okay,
Yes. Yes.
comes from the fact you have two watches in A. And the other one, which is the blue one, this square here, comes from the fact that you have two watches in B. Okay?
So the probability that we collect two watch in A is 0.99 square multiplied by a half.
Yes. Plus 0.995 square times 0.5. Okay. And I get something like 0.98. So this is equals to 0.985, etc. Okay, we don't care the decimals here. Is it clear for you? This is the numerator of the fraction.
Okay. I think that is what Alban is saying, that okay.
Alban, you have a question?
No, I just wrote as a comment that I think that Fred is saying that we are picking a watch, but we don't like put it back in the set before taking the second one. So it must like have an impact on the second probability when we
Yes.
do the experience the second times.
It's what I was saying.
Like it's un tirage sans remise.
It's why the first time is 0.99 and the second time is remaining only 99 watch. So
Yeah,
if,
the probability do not change. You take two. You take the two at the same time.
okay.
Okay, so that's for the numerator. Now, what can be said about the denominator, which is this guy, okay? The brown guy. So the brown guy is just the probability that x equals to 1. Wait. What? Wait, I'm a little bit confused here. No, yeah, that's right. So this is the denominator, this is the numerator. Okay. Now, the probability of x1 equals 1 given x1 is equals to 1 is that thing, and the probability that x1 is equal to, actually here there's an equal there. Okay, times the probability of A times the probability of B. Okay, I think that's okay. Now, on the other side, okay, on the other side, we have that the probability that x1 is equals to 1, okay, that is the brown denominator. Again, using the total causes formula, you get that this probability is equals to, well, just the probability of x1 equals 1 given A times the probability that given y equals A, sorry, y equal A times the probability that y equals A, and again plus the probability that x1 is equal to 1, yeah, given that it comes from the B factory, multiply by the probability that the factory is B. Again, you replace by the numbers and you get something like 0.5 times 0.99 plus 0.5 times 0.995. And if I take my computer, I put on Python 0.5 times 0.99 plus 0.995. This is 0.9925. Okay. So you have to compute those two things. The first is the denominator, and sorry, the first is the numerator, and the second one is the denominator of the fraction. So finally, you can come back here and you get 0.985 divided by 0.9925. Okay, and we get, I don't know how many, that thing divided by that thing. equals to 99. This is equals to 0.992506 if you want to be very precise. Okay, and that was the answer to the exercise that we started last time.
Thank you.
Any other question? Any other question?
No, it's okay.
Perfect. Okay. Okay. Last time we start talking about random variables, about expectation. We give some formulas and some properties for the expectation. Okay. And I want to talk now about the mean and the variance. Okay. Mean and variance. Mean and variance. Okay. So in French is moyenne et variance. Okay. And we have here a definition. Okay. That says that let X be a random variable such that the expectation of the absolute value of X is finite. Okay. When this happens, we say that X is integrable. Okay. X is integrable. You will understand later why we say that. Okay, so let X be a random variable such that the expectation of the absolute value of X is a finite number. Okay. In this case, and only in this case, we define the mean mu of the random variable X is mu of X defined by the expectation of X. And this is equals to the sum of n probability that X equals n from n equals 0 to infinity. Okay. So usually people use the word mean and average as equivalent. They are equivalent. If you say the average of something, the mean of something, it is equivalent. But the expectation implies that we know that this function X is integrable. Okay, please remember that X is a random variable. That means that maybe this is similar to omega. It's not an omega, it's an R random variable. X is a function from omega to a set E. Okay. And later we will see why this is integrable, because we actually integrate the random variable with respect to a probability measure P of omega. Okay, but this is later. Don't worry about that right now. Okay, so in that case, if the expectation of the absolute value of the random variable X is finite, then we call that number the mean. Okay, and we use the Greek letter mu. Okay, perfect. Now we have something important to say. Important here. Important. Something that I will denote quickly as L2 of omega is inside L1 of omega. Okay, those guys, later we will see they are the Lebesgue spaces. And actually, this is not true if omega is a non-bounded set. Okay, but it's true in probability cases. That means with finite measure spaces. What is L1? L1 of omega is the set of functions f defined from omega to r. Okay, but not only that, such that the integral of the absolute value of f of x dx in omega is finite. Okay. Let's try some questions. For example, Caroline, are you with us?
Yes.
Yes. Can you please tell me if I consider the following function, f of x equals 1 over x, and omega is the interval 1, 3. Okay. Is this function in L1? Is f in L1 of omega?
Yes.
Yes. Why?
Because the how do you say the
You can say it in French if it's easier for you. How? Comment? What's the condition you verify to ensure that this function is in L1?
it's when the absolute value.
Voilà, donc on doit. Yeah, you have to. You ask, is this integral finite?
Yeah.
And how do you know this is finite?
Is what?
Finite, fini. Comment tu sais que cette intégrale est finie? Elle converge.
We just have to do the
Yes.
primitive.
Yeah, the antiderivative.
Antiderivative.
What's the antiderivative of 1 over x?
It's 1 over x squared.
No. Someone? Maxence, what's the antiderivative of 1 over x?
ln de x.
Yes, the natural logarithm of x. Okay. Okay, so this this integral is actually equals to the natural logarithm of 3, which is a finite number. Okay. So that's why this function f is in L1. Okay. Is it clear for everyone? Okay, let's try another one. Maybe Alban. Are you there, Alban?
I'm there, but I wasn't really listening.
Okay, so the question is, if you take this function 1 over x squared and you take the interval 1 plus infinity, is this function in L1?
Yes, because of the square.
Can you please explain a little bit more?
No, I think I'm not sure about it at all.
You say because of that. Really? Yeah. The answer you said is the good one.
I said that because of the definition of L1 just above, like because of the absolute value.
Yeah, I mean, this is a positive function, yeah, on
Yeah.
1 plus infinity. So the absolute value of 1 over x squared is just 1 over x
1
squared.
over x squared.
And we know by, when you were at second year, I think, you saw the Riemann integrals. The Riemann integrals that are the integrals of the form 1 of x power alpha from 1 to infinity. And those integrals converges if alpha is greater than
1 alpha.
1.
Oh.
Okay. If alpha is bigger than 1, strictly bigger than 1. Okay. Well, something that is here is this remark. If we are concerned about finite measures, and that is always the case in probability theory, in that case we have some inclusions of integrable spaces. Okay, that means that this is L1. It's the bigger one, the biggest. Then you have L2. Then you have L3. And at the infinity, you get L infinity. Okay. We are going to come back to this later. So don't worry, I am not asking to you to understand everything, but this is something that definitively you will need to understand fine in some weeks. Okay. So you have this inclusion of spaces. So those are spaces of functions. Okay. Functions defined from omega to R. Okay. And what's that type of function? Well, random variables. Okay. We are interested in this course on random variables. Of course, this can be much more general, but at least if we restrict ourselves to random variables, real random variables, we are dealing with functions from omega to R. And in that case, we can define some structure of random variables according if they have moments that are the mean, the variance. Okay, so for example, if my random variable x has a mean, she will be living here. Okay, and we say that that's the first order moment. But there's a more VIP class of random variables, which is those who has a second order moment. They live here. It's a more restricted class, okay? It's more private. Those has a second order moment. Then more again, it's a smaller space. You have less people here in L3. This is the set of random variables that has a third order moment. Okay, the mean, the variance, etc., etc., etc. And here you have the random variables that possesses an infinite number of moments. Okay. Well, don't be afraid. We are going to talk about this later. But I have a remark. We talked about this because this remark, but it's an important remark. We have an inequality that says that the absolute value of a number A is smaller or equal to 1 plus A squared. Okay? If you take the absolute value function is something like that, okay? This is the absolute value function of x or a, okay? Absolute value of a. And you can see that this function is always smaller than 1 plus x squared, okay? 1 plus a squared is this parabola here. Sorry, no, not that one. Is that one? Well, you understood, no? I can't. Well, you have a parabola here. This is 1. This is 1. And here you have 1 plus a squared. Okay, since this inequality is true, since this inequality is true for any a in R bar, okay, any positive, negative, or infinite number, we have that the absolute value of x, as a consequence, we have that the absolute value of a random variable x is smaller than 1 plus x squared, okay? And therefore, if you integrate this inequality, okay, if you integrate, you get that the integral, or if you take the expectation is the same. If you take the expectation of the absolute value of x, this will be smaller than the absolute value of 1 plus x squared, but the expectation is linear, so the expectation of 1 plus x squared is just the expectation of x squared plus 1. Okay, this is equals to the expectation of x squared plus 1. Okay, what can you conclude from this? It means that if this is finite, okay, 1 is obviously a finite number, okay? So this guy is finite. But if you can prove in some way that this is finite, then by this inequality, this guy will be finite too. Is it clear for everyone? From this inequality, absolute value of a smaller than 1 plus a squared, if I take the expectation of this inequality, and the expectation, you know, it respects the order of the inequality, then I get that the expectation of the absolute value of x is smaller than something which is the expectation of x squared. So if this is finite, then automatically this will be finite. Okay. Then that means that, in conclusion, if a random variable x is such that the expectation of x squared is finite, then, okay, x is integrable. That's an important remark. Super important. If the expectation of x squared is finite, then our random variable will be integrable. Any questions about this or something before? Is it clear? Okay. Now, a second definition, which is the variance definition. let x be a square integrable random variable, its variance is by definition the quantity sigma square, okay, defined as the expectation of x minus the mean square. Okay. This can be also computed if you express this expectation as a sum. This is no more than the sum of n minus mu square times the probability of x equals n. And this sum goes from 0 to infinity. Okay. There's another thing which is very, very classical. What happens if you develop the square? Okay. So you take this guy and you develop the square inside. So this is equals to the expectation of x squared minus 2 mu x plus mu square. And the expectation is linear. So this is equals to the expectation of x squared minus 2 mu times the expectation of x plus the expectation of a constant, which is itself, plus mu square. And this is the expectation of x squared, which is something, minus the double product of mu times mu, it's mu square, plus mu square. This is this guy and this guy are the same. So finally, you get the expectation of x squared minus the mean square. Okay. So the mean is the center of inertia of a random variable. Okay. For those who don't speak French, center of inertia in French is said centre d'inertie. Okay. La moyenne, c'est le centre d'inertie de la variable aléatoire. C'est le centre de masse. It's the mass center. Okay. Any question?
Yes.
Yes, please.
For the last line, it's expectation of x square.
Yes. Yeah. Thank you.
Intérieur.
Thank you very much. Yeah, you're right.
Okay. Thank you.
Thank you. Thank you. Thank you. Any other remark or questions? You know, this first chapter is a lot of definitions, but we need to get all the vocabulary, the basic vocabulary, to then start doing math. Okay. I know for the moment it's not very exciting. It's a lot of definitions, but later we will see some theorems. Okay. Some applications, some things.
Can you explain, please, again, why the expectation of x is equals to mu?
That's a notation. If you remember here, mu is the letter we use for the expectation.
Oh, okay.
Okay. Perfect. So now we can start talking about independent random variables. Independent random variables. And again, we have a small definition. What does it mean? That two discrete random variables are independent. So let x and y be discrete random variables. We say that x and y are independent. If the probability that x equals y, and y equals j, this is not a conditional probability, it's just the probability that x equals y and y equals j is simply the probability that x equals I and the probability that y equals j. Okay, and this equality has to be satisfied for any I, j in E. Okay, E is the x and y's are from omega to E. Again for y. Okay, that's the definition of independent random variables. That means that the events, this one, and those one are independent. You know, those two events are independent because the probability of the intersection is the product of probabilities. Okay, so we define the independence of random variable using the definition we already have for the independence on sets, on events. Okay, any question? Okay, so just to clarify the thing, this is a shorthand notation. The comma here is a shorthand notation for the set x equals y I intersected to y equals j. Okay, so this green thing here is the same as this black here. Okay, it's just a more simple notation, a comma. But that means the set of omegas such that the image by x is I, and the set of little omega in capital omega such that y of little omega is j. Okay? Well, you can generalize, of course, this definition to n random variables. Okay? You are not restricted to only two of them, so you can just use this little generalization. Okay, so it's a black generalization. I will say that the x1 is independent of x2, independent of xk. Okay, those k random variables are independent if for any I1, I2, Ik in E1, E2, Ek, okay? You have the Cartesian product here. The thing you can imagine, the probability that x1 equals to I1 and x2 equals to I2 and etc. xk equals to Ik, this probability is just the product of the probabilities xk equals ik. For k equals 1, well, I used it k here, but it's actually p or whatever. Xp ip for p equals 1 to k. Okay. It's just the generalization of the formula before. Okay. This simple formula for two random variables, you can generalize its definition to the case of n random variables. Okay. Perfect. Now, what's the generalization of an arbitrary number of random variables? Maybe Albin, I know Albin like this kind of question. So Albin, if I generalize from 2 random variables to k random variables, what's the generalization that follows?
Wow, I don't know.
An infinite number of random variables. Okay? Because here I have k random variables, a fixed number. The next generalization is an infinite number of them. Okay? This is very important because a sequence of random variables is something called a stochastic process. Okay? And stochastic processes are very, very useful for a lot of applications, going from error detection to, for example, finance. Of course, in finance, they use a lot of of stochastic processes, economics, biology. Okay. So definition, this is the last generalization. We actually can generalize even more, but we don't care about that. Okay. A sequence, hein, donc une suite en français, in French, suite. A sequence xn for n bigger than 1 of discrete random variables, taking their values on sets n bigger than 1, respectively. Okay, that means that x1 take its values on E1, x2 on E2, respectively. I don't know if there's double L in respectively. I think maybe no, but well, doesn't matter. Is independent. Yeah, I'm almost sure there's just one L here. Is independent if, okay, and that's the difference with the thing before. If any finite collection of distinct random variables, random variables, okay, x I1, x I2, blah blah blah, x IR. So you take R random variables from this collection, okay? You pick up R of them, is independent. Okay. So you have an infinite number of random variables. If for any finite collection of distinct random variables, they are independent, then you will say that this sequence is independent. Okay. Now, there's a very important word you will meet, I don't know, maybe 1 million times in your life, if no more, is the identically independent, identically distributed, IID. In French is the same, indépendante, identiquement distribuée. This is a particular type of hypothesis that is used all the time, essentially because this is the simplest case. If it's not IID, people don't know how to do a lot of things. So IID means independent, okay, independent, identically distributed. Independent, identically distributed, okay? And this is the case when all the sets are the same, and if there is an independent probability distribution function that does not depend on n, okay? So I have maybe 2 random variables, maybe I have 10 of them, or 1,000 of them, or even an infinite number of random variables, then the independence is defined in this way, okay? That's the independence. Maybe we can try to do something here. Let me check if I have a good exercise for you. Maybe later. I want to go directly to the types of random variables, and then we will come back to some examples, okay? Because all my examples use some particular random variable. Okay, well, let's continue, okay? IID. Any question? Okay. Okay. Now, conditional independence. Conditional. I'm sorry. Conditional independence. Do you remember what does it means that 2 events are conditionally independent? Maybe I can ask to Lucas Chenel. Please, Lucas, can you recall us what's the definition that A and B are conditionally independent given C?
Yes. I don't know.
Hein, qu'est-ce que ça veut dire que 2 événements sont conditionnellement indépendants?
Je peux le faire en français ou pas? Ça vous dérange?
Oui, non, vas-y.
Si la probabilité de A inter B sachant C égale la probabilité de A sachant C plus la probabilité de B sachant C, je dirais. Ou fois, je sais pas.
Attends, quoi du coup?
La probabilité de A sachant C fois la probabilité de B sachant C.
Yeah, that's precisely the answer. Okay, that's the conditional independence for events. Perfect. Okay. Now we want to define the conditional independence, not for events, but for random variables. Okay. So, Luca, consider that you have X, Y, and Z. So here we are trying to give a definition. Let X, Y, and Z random variables, okay, taking their values, on the sets EFG, respectively. Okay. Can you please define what does it mean that X and Y are conditionally independent with respect to C? Okay. X and Y conditionally independent given Z. What does that means?
Et on a...
Donc c'est toujours un peu la même chose en mathématiques. On définit des petits briques de base et ensuite les briques suivantes, on les définit en termes des briques précédentes. Pour le moment, for the moment, the only conditional independence definition we have is for events.
Yes.
And we want to generalize that to conditional independence of random variables. So you need to come back to the events in some way.
I don't know. C'est un peu pareil. On écrirait P de, par exemple, la probabilité de X égale grand X égale petit x. Et grand Y égale petit y, sachant que grand Z égale petit z, égale à, du coup, notre probabilité de X égale petit x, sachant grand Z égale petit z, fois la probabilité de Y égale petit y, fois, sachant grand Z égale petit z.
Très bien. Yafemeod, excellent. Okay.
Thank you.
Excellent. That's the definition of conditional independent random variables. Okay. And every time you see a new concept, try to figure out how this concept comes from the basic ones you know already. Okay. Yeah. So I think that's all. Any questions about conditional independence? Is it clear? Okay. If you want, we can make a 15-minute pause. Okay. So it's 3:11, so we can come back at 3:25 or 3:30. Okay. Is it good for you?
Yeah, it is. Thank you.
Yes.
Okay. See you in 50 minutes. Okay. Are you there? Is everybody there? Alors, let's ask one by one. Is Arthur here? No. It seems that Arthur is not here. I have 1 minute more to take my coffee. You know, mathematicians, we are machines that transform coffee into theorems. That was Paul Erdős, a great Hungarian mathematician who used to say that. And this is a very good coffee. It seems it's one of the best coffees from what's this country? Ecuador? I think it's Ecuador. Okay. Okay, conditional independence. Any question about conditional independence? Adrien Villemain, is it clear?
Yes.
Yes?
Yes, perfect.
Okay, perfect. Can you please, Adrien, maybe motivate this computation with an example? Can you imagine 3 random variables, x, y, and z, such that it would be nice to know if yes or not they are independent?
Yeah, probably we can take an example with like we got a bag with some colored balls, and we take one out, and we got like a number of points, and depending on the first ball we got like on the second time we put out a ball, we got like another number of points. It might be a bit complicated, but
yeah, maybe try something more.
Okay.
I don't know, with people, you know, like the height, the weight, and the astrological sign, for example.
Okay. Well, for the astrological sign, it can be with the dates that both are light. So if you born like in July, you are like a Cancer or things like that.
Yeah,
so it depends on the probability of when you born, you get the astrological sign.
I was actually thinking more on something like, what's the probability that a person is, I don't know, 1.85 meters and is 70 kilograms, given that it's, I don't know, what's a nice sign? I don't know, whatever, okay? Given a particular sign.
Okay.
So this is the type of computations you can answer to, or you can ask, is this independent? Is the weight and the sign, the weight and the height independent, conditionally independent to the sign? Okay. Well,
yes.
that's something interesting. Maybe I can make something to draw something. Here you have a bunch of people. Okay, you have a bunch of people there, and each person there has a height and a weight. Okay, something here in kilograms and something here in meters. And we say, okay, if X is, I don't know, the height, and Y is the weight, we want to know if height and weight are independent conditionally to the Z zodiac sign. Okay, that's okay. This is very strange, but this is a type of computations we can try to figure out. If we want to give something maybe more interesting, much more realistic than this, X can be, for example, the price of oil. Okay, the price of oil when you go to the with your card and to fill the reservoir of your car. X is a random variable. It can be 1, it can be 1.32, wherever. And Y will be, for example, the number of born people, okay? Number of borns in a particular moment. Okay, so I want to know if the price of the oil is independent on the number of new people arriving to the world, conditionally to something interesting, okay? For example, conditionally to, I don't know, maybe the continent, where I want to invest. I want to invest. You know, this type of computations, economists are very, sorry, I have to answer a message. Yeah. So I was saying this type of computations or this type of questions arises very, very often in economics, okay? You have different variables and you want to know if they are independent or not. And if they are not independent, what is the relationship between them, okay? Okay, perfect. So that was the slide for conditional independence. Now we have an important formula for the expectations. Okay, so this is a theorem. So theorem, let Y and Z be two discrete random variables, be two discrete random variables with values in the countable set F and G. F and G respectively, and let V the function from F to R bar, okay, it can be infinite, and W the function that goes from G to R bar, okay. Those functions are either non-negative or V of Y and W of Z are integrable, okay. Okay, positive or integrable, okay. But that's not the important thing. The important thing is the conclusion. Then the expectation of V of Y times W of Z, this is actually equal to the expectation of V of Y times the expectation of W of Z. Okay? So as you know, Y and Z are random variables. That means that they are defined on omega and they go into F, and the same for Z. Z goes from omega to G. Okay. And then you have those functions V and W. V goes from F to R. Okay. V goes from F to R bar. And W goes from G to R bar. Then naturally you can have the composition of those two functions that goes from omega to R, which is V of Y, and here to here is W of Z. Okay, and the thing we say is that if you compute the expectation of the product of this one with this one, then you get simply the product of...
Non.
Non, mais t'en as un où tu sais, t'as un petit chien et un gros chien. Et tu sais, le gros chien, tu sais, ils l'ont fait un peu musclé. Alors, ils ont fait des petits bras musclés en mode les deux personnes d'une seule chose. Et puis, c'est lui qui est minuscule, lui. Et c'est vrai que. Et voilà. Hein. Non, hier, on a un peu prié pour.
Okay, so you have the product of this one with this one, okay, which is equal. So the expectation of the product of these two random variables is simply the product of the expectations, okay? Any question about this? Any question about this theorem?
Doesn't it only uses the linearity of the expectation?
Yeah, very good question. Why is this true? Okay, why is this true? Well, if we really want to know why this is true, we have to prove it. Okay, normally I don't take too much time to prove things, but today I will. Okay, so let's do the proof of this theorem. So proof. We are going to define a random variable. Okay, so let x, I introduce x. Let x a random variable with values, discrete random variables with values in the countable set E, which is defined by the product of F and J. Okay, so I have two random variables. I'm going to construct one from those two, okay, which is a vector, okay, with values in the countable set defined by x is just y and z, is the couple, okay? And consider the function g that goes from E to R bar, defined by g of x is simply the product of v of y times w of z, where x is the couple yz, okay? Little x, little y, little z, okay? So I actually unify the two random variables into one, okay? Now, I can apply the standard definitions of the expectation. Okay. I have that the expectation of the complicated thing, which is V of y times W of z. This was complicated. Now it's very simple because this is just the expectation of g of x. Okay. This is the expectation of g of x. And by definition of the expectation, this is actually equal to the sum for all the x in E of g of x times the probability that x equals to x. Is it clear for you? You take the complicated thing, you construct useful notations to simplify the problem, and now you say simply that the expectation of this product is just the expectation of this j function applied on x. And by definition of the expectation, we get that. Now, this sum, okay, over x is actually a double sum because you have x, which is, it has two components. It's a sum on y, which is in f, and it's also a sum of a z in g. Okay, and it's a double sum then, okay, it's a double sum of v of y. Salut Eric. V of y times w of z times the probability that y equals y and z equals z. Okay. This is just I come back to the notation. Looked at this event, okay, these random variables. I suppose that the probability of the intersection is the product of the probabilities, okay, because they are independent, okay. I can say then that this is the same thing, exactly the same thing, but with the product of y equals y and z equals z. Capital Z equals little z. Okay. Now I distribute the sum. This double sum normal. I don't know if you normally, yes, you saw this type of things in your first year at school. This double sum can be written into a product of sums. Okay. I'm almost sure for those who were here with the math teacher Winston, you saw this. This is called the produit de Cauchy. Okay, so this is the sum for y in f of v of y times the probability that y equals y and the sum of z in g of w of z times the probability of z equals z. And of course, we find that this is the expectation of v of y times the expectation of v of z. Okay, and that's the end of the proof. Any question?
Yes. To go from the second line to the third, do you have to prove that y and z are independent?
Yes. Yes.
And how do you know then?
How do I know they are independent?
Yes.
Well, because I assume they were independent. It's by I add that to the hypothesis in the theorem, you know.
Okay. Okay.
Let X be yeah, you're right. Sorry. Independent random here. Independent discrete random variables.
Okay.
Okay. So since they are independent, I can use this property here. This green thing is equals to that green thing. Okay.
Okay.
Thank you for the advertising. Any other question, please? No? Is it clear for you all? Do you think it's too fast? Is too slow? Is too easy? Too difficult? I want to get your feedback. For example, what do you think, Mohammed Shukri Bouziani?
I think I would need to watch the replay one time at least.
Okay.
But it's okay.
Okay, perfect. It's not too fast?
No.
Okay. Thank you. Okay. From this theorem and this proof, we have a corollary. Okay. A corollary is a simple proposition that can be deduced directly from the theorem. So here, corollary. If you have n independent integrable random variables, let x1, x2, xn independent integrable random variables. Okay. With values in n. That means that the image set is the natural numbers. For example, x1 can count the number of votants, okay, into the elections. X2 can count the number of ants in the kitchen, whatever, okay? It's a natural number, okay? Then the variance of the sum of the random variables is simply the sum of each of the variances of the random variables. Okay, so we can summarize this as variances add up. Okay, les variances s'ajoutent. So if you want to compute the variance of a sum of random variables, then you only get the sum of the variances of the random variables. Okay, of course, please do not forget the hypothesis, which is independent integrable random variables. Okay, you can try to prove that if you want, okay, as an exercise. I don't know, maybe right now or maybe another day. I think that can be useful. I don't know. Do you want to prove this now or do you want to prove this as a homework? You don't have an opinion. Okay. What time is it? It's 4. We have 1 hour. Okay. Let's give this as an exercise for later. Okay. Homework. Prove that homework. Okay. That's the end of the basic things. Now we can start talking about famous discrete probability distributions. Okay, so this is like chapter number 2. Famous discrete probability distributions. Discrete probability distributions. If I flip a coin, okay, you have a coin here. What's the name of the distribution when I flip a coin? Anyone?
Distribution binomiale.
Non, un truc encore plus simple.
Uniforme.
Non plus.
Bernoulli.
Très bien. Bernoulli. C'est qui a dit ça?
C'est moi, Adrien Dubois.
Vous avez un point supplémentaire pour le contrôle.
Yes.
La Bernoulli. OK. La Bernoulli, B of P, is maybe the simplest probability distribution you can think about. What does it mean when I say that a random variable x follows this probabilistic law? Well, that means that you have two possible values for x equals k. K can be either 0 and 1. Usually 1 is denoted also called as success. Fail, success, 0, 1, wherever. And the probability that x takes the value k is p. So now, Mrs. I don't know who, maybe Caroline, can you please tell me if the probability that x takes the value 1 is p, what is the probability that x takes the value 0?
It's 1 minus p.
Perfect. 1 minus p. Okay. So this small table is what is called the law of x. And this is the Bernoulli law. Now, you can make a plot for this law, a very simple plot. In the x-axis, you put k. And in the y-axis, you put the probability that x equals k. So you have two possible values, 0 and 1, 0 and 1. And for those, you have p 1 minus p. If p is 1/2, then 1 minus p is 1/2 too, and we get a uniform distribution here. That's in the ideal case that the coin is not a tricky coin. But if you have a tricky coin, maybe it's more likely to have a 0 value than 1. And in that case, this is p, and this is 1 minus p. Or of course, if this is p, this will be 1 minus p. Okay, you get it, I think. So depending on the value of p, it is more likely to take 1 or 0. Okay, so that's the Bernoulli distribution. Bernoulli. Now, you can compute for the Bernoulli distribution the expectation and the variance. So what is the expectation of X? Well, it's just the sum of K times the probability that X takes the value K for K equals 0 to 1, because I have only two values. So this is 0 times the probability that X takes the value 0 plus 1 times the probability that X takes the value 1. Okay, so 0 is here. Probability that X takes the value 0 is 1 minus P plus 1, which is here, times P. So when you add up, this is just P. Okay, so the expectation of a random variable that follows a Bernoulli distribution is P. Now, what about the variance? Variance of X, which is also sigma square of X. By definition, this is the expectation, okay, variance, the expectation of X minus the expectation, or mu, okay, because we know that this is finite now, square, and we know also that this is the expectation of X square minus the expectation of X square. Well, we know now that the expectation of X is P, so this is just minus P square. And what is the expectation of X square? Well, it's the same. You take the square values here, so you get 0 again and 1, because 0 square is 0 and 1 square is 1. And when you compute the expectation of that variable, you get 0 squared times 1 minus P plus 1 squared times P. That's just P. Okay? So finally, the variance of my Bernoulli law is P minus P squared. And you can factor this polynomial and say that this is P times 1 minus P. This expression, X times 1 minus X, you will find this expression often, okay? Also for differential equations, this is the logistic term. And maybe you remember I say that the solution of this equation is the sigmoid function, which is useful for the activation of neural networks. Okay, so this quantity, something times 1 minus something, comes often in mathematics. Okay. Any question about this computation? Is it clear? Really, feel free to ask. If it's something you don't understand in this slide, please tell me. No, it's perfect. Okay, good. Now, the sister of this Bernoulli distribution is another distribution called binomial. Okay. And the binomial distribution is just the repetition of n Bernoulli launches. Okay, that's the case. So you have your coin, you launch and you get, for example, 1. You launch again the coin and you take maybe 0, 1, 0, maybe 1, maybe 1, whatever. Okay, you take your coin, you flip it a number of times. How many times? N times. Okay, N times, and you have probability P of getting a success. So the binomial distribution BNP is a probability law, okay, that depends on two parameters. X follows this law, okay? So with respect to the Bernoulli distribution, here I have only one parameter. Instead, for the binomial one, I have two parameters, n and p, okay? And x represents the number of success. This is the number of success after n plays. Okay, so you launch your coin n times and you get a certain number of coins of success. Okay. Now we want to know what's the law of this variable x. So what do we have to know? Again, as before, we have to know the entries of this table. Oops. I have to know the entries of this table. I have here then x equals k and the probability that x equals k. And here the probability that x takes this value k. So k can be, okay, let's ask something. Someone, sorry. Maybe, I don't know, maybe Loris Le Métayer.
Yes.
So x is the possible number of success.
Okay.
After playing n times. What's the minimal number I can have?
So x is the what you said. What is the minimal number of success?
Yeah. What's the minimal value for x?
It's 0.
0. Perfect. And what's the maximal value?
N.
N. Perfect. Okay. Can you please tell me what's the probability of getting 0?
The probability of getting 0.
Yeah. You know, for example, that means if I have 0, that means that I have this. Sorry. If x is 0, the only possibility to get a 0 here is that I have 0, 0, 0, 0, 0, 0, 0 n times.
Yes.
What's the probability of this? You know, you have to count how many possible words of n letters, because here you have two letters, letter 1 or letter 0. Okay, so you have two choices for each small box here. So how many choices you have at the end? If here you have 2, you have 2 here, you have 2, 2, 2, and 2.
So 2 power n.
Yes, 2 power n. Okay. For now, I assume that the coin is just equilibrated, so p equals 1/2. So if I assume that, I get 1/2 power n.
Okay, I see.
Okay.
Okay.
And it is the same if I ask for n. Why? Because if I get n, that means that I have 1, 1, 1, 1, 1, 1, and there's just one possibility for constructing such a word with only ones among 2 power n.
Okay.
Okay.
I see. Yes.
Now, a little bit more difficult. Again, assume that the coin is equilibrated, so you have 50-50%. What's the probability that x takes the value k with any k between 0 and 1 and n? You see what happens? You have k ones. Okay.
Yes.
You have k ones.
Yes.
If k is equals to 3, it can be those 3, or it can be those 3, or it can be those 3. You have to pick 3 of them among n. What's the name of that object?
Oh, it's a combination.
Yes, it's the combinations of k objects among n.
Yeah.
So it's the binomial coefficient kn.
Yeah.
Okay.
Remember now.
So,
It's,
so this is the binomial coefficient.
yes. Okay.
Binomial coefficient. And if you don't remember the definition of this guy,
It's. I think I do. But
yes, please.
I think it's. How do you say factorial?
Factorial.
Factorial n divided by factorial k times factorial n minus k.
Yes, perfect. Thank you very much. Yeah, you get that. Okay, thank you very much, Loris.
No problem.
Okay, so the binomial distribution is I am launching n times a coin, okay, and knowing the probability of having a particular number of success depends on the number of ways I can put k times the number 1 inside my word. Okay, so I have to choose k objects among n. Now, this was the simplest case when p equals 1/2, but if you now add the general case, the general case, you have this result. Okay, so in general, the probability that my random variable x, where x is a binomial distribution with parameters n and p, equals k, is actually k among n by binomial kn times the probability power k times 1 minus p probability of n minus k. Okay? And I'm almost sure, 100% sure, that you all know what's this guy. Who is this guy? Maybe I can ask to Thibault Lejoux.
Yes.
Who is this guy, Thibault, the blue guy? What's the name of this guy? You can say it in French if you prefer.
Je sais pas.
It's the coefficient binomial. Okay? Ça vient du binôme de Newton. Coefficient binomial ou binomial. Binomial. Okay? This guy comes from the Newton's binomial. Okay? It's, I think, it's easy, but let's say it again. Maybe I can ask, who I didn't ask today, Oriane. Okay? Are you there, Oriane?
Yes.
Okay. What's a plus b power 1?
A plus b.
Yes. What's a plus b power 0?
1.
1. And a plus b squared?
A squared plus 2ab plus b squared.
Yes. And the last one, a plus b cube?
A cube plus 3ab
a square b plus
plus
3
3
ab square plus
b cube.
b cube. Okay. Albin, what is a plus b power 4?
A power 4 plus 4a cube b plus 6a cube a square b square.
Yes.
Plus 4ab cube.
Yes.
Plus b power 4.
Power 4. Okay. Let's analyze a little bit those formulas. At the beginning, they start always by a power the thing we have. Here the exponent is 3, so we start with 3. Here the exponent is 4, we start with 4. Now look at the powers of a. They are decreasing. You have a power 4, a power 3, 2, 1, 0. 3, 2, 1, 0, 2, 1, 0. Okay, so the powers of a are decreasing, starting from n and going up to 0. Now, what happens with b? The powers of b are increasing. 0, 1, 2, 3, 4, 0, 1, 2, 3, 0, 1, 2. Okay, so we know what happens. Now, look at the coefficients. That's the thing. How do I get this 6? Well, it's just 3 plus 3. Okay. How do I get this 4? Well, it's just 1 plus 3. How do I get, let's say, this 2? It's just 1 plus 1. Okay. Is it clear, the thing? So if you take the general case here, and you say a plus b power n, this is something with a, something with b, because we have a power something, b power something, and a coefficient. Okay, and we have a sum because we are adding things, you know, this plus, 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 plus. So we have a sum of some coefficient, which is the binomial coefficient, k among n, a power k, b power n minus k, for k going from 0 to n. This is the Newton's binomial. Okay, and the magic is in the coefficients. You start with ones, and you write 1, 1, 1, 1, 1, 1. Okay, is this one here, and then you end with ones also. So you start with ones and you end with ones. In the first, in the top, we have just one number. In the second one, we have two numbers, a plus b. Now I have to add up the two before. So I have to add this with this to get this one. So 1 plus 1 is 2, and then 1. Then 1 plus 2 is 3. 3 plus 1, sorry, 2 plus 1 is 3, and I end with 1. So here I get 3 plus 1, 4, 3 plus 3, 6, 3 plus 1, 4, and I end with 4. Okay? So now maybe Victor Kuffel.
Yes.
Can you please give me this next line here?
5.
Yes.
10.
This.
10.
This.
5.
5.
1.
1. Perfect. Okay, so now you know how to compute a plus b power 5. A plus b power n is this sum here. And look, if you come back to our binomial distribution, the probability that my binomial distribution, my random variable x that follows the binomial distribution takes the value k, it is the binomial coefficient k among n times p power k times 1 minus p power n minus k. Okay, this thing here with a equals p and b equals 1 minus p. Okay, is it clear? It's quite easy, no? It's not very profound. So this you have to remember. Okay, this is very, very important, and you have to memorize this thing. Okay, that if x is a binomial random variable, then the probability that x equals k is k among n times p power k times 1 minus p power n minus k. Okay, perfect. We can also, okay, let me show you something here in my computer. Default, yeah. Okay, so show the screen number 1. Do you see this this white part?
Yes.
Okay. Perfect. So I want to make the discrete plot of something called the probability distribution function, okay, for the binomial distribution. Okay, so you know, in this course and generally in the data engineering major, we always use Python, but you have a lot of other interesting scientific software you can use. I suggest to you to learn as much as you can for other languages. You can, for example, know how to use C++ or R is very important for statistics. And there's other type of languages more related to formal computations and other type of computations as Maple or Wolfram Mathematica. So the examples I'm going to show you here are from Wolfram Mathematica. Okay, so if you use the function binomial distribution NP, this will construct a random variable using those parameters. Okay, now I can ask for the probability distribution function, the PDF, with value k. Okay, so this is exactly that thing. This blue formula, it is exactly that. Okay, so it's p power k, 1 minus p power n minus k, and the binomial coefficient nk. Okay, now I want to make the plot of that function. Okay, so I'm going to make a discrete plot of this situation, and for k going from 0 to n. Okay, and since this is a formula containing a lot of parameters, I have to manipulate them. Okay, so I say manipulate this thing for I don't know, maybe n can be a number like 100, maybe, yeah, 30 up to 100, and p is 1/2 coin, but it also can goes from value 0.9 to 0.999. And yeah, okay. So this is what you get for a binomial distribution. Okay, so you have a maximum of probability in the middle. Okay, and the probability is lower here and lower here. How do you interpret this? Well, it's quite easy because x is the number of times I get 1. So if I launch 30 times the coin, I am not really expecting a slow number of ones. It's also maybe not also likely to have a big number of ones, like 30 times I get 1. This is not really likely, but it's very likely to have a middle number of them. Okay, and as you can see here in X, you have the value of K. Maybe I can actually add the access. Access label is K, and the probability that X equals to K. Okay, oops. Right, this is a weird keyboard. The probability of X equals K. Yeah. Okay, so here you have K, here you have the probability that X equals K. If the parameter P changes, okay, do you see what makes to the curve? P is the probability to get 1. If P is higher, okay, I am expecting to win more times because P is bigger, okay? The probability to get 1 is bigger. If P is slow, that means that the probability of getting 1 is slow. I am expecting this type of behavior, okay? Is it clear? Any question about that? No? Okay. Perfect. Perfect. What time is it? 4:23. We still have half an hour. Okay. Now, we have to ask what are the expectation and variance of binomial distributions. Okay, so this is a theorem. If X is a binomial with parameters NP, then the expectation of X is just N times P, and the variance of X is N times P times 1 minus P. This is something that you can remember easily because the expectation and variance for a Bernoulli distribution is P and P times 1 minus P. So if you want to pass to the binomial one, you add N. Okay, you multiply by N. Okay. And as an exercise, you have to prove this. If you understood well this, all the things we saw today, please prove this for yourself as a homework. It's very easy, and if you don't, if you are unable to prove it, you can check on any probabilistic book. There are a lot of them that are very good. Okay. If you want some references in good probabilistic books, it depends if it's more in English or in French. In French, there's one I really like. which is from Walter Appel. Walter Appel. The name is Probabilité pour les non-probabilistes. Probability for non-probabilists. Probabilité pour les non-probabilistes. Okay, this one is very, very, very good. It's very nice to read it. And another one I want to, actually I was trying to buy it for you, but I didn't succeed. The other one is Bernard Bozamy. Bernard Bozamy, and the title is Méthode probabiliste. Méthode probabiliste pour l'étude des phénomènes réels. Those two are very good. Of course, you have a lot of probabilistic approaches. Each book uses a different one. It depends on what do you want to learn, okay? And in English, there's also a lot of very good books, but I don't have them here at my office. They are at my place. Yeah, I think they are not here, but let me look on the internet, the title. Yeah, so it's, I mean, yeah. This one is very nice. I want to show you the image directly. Okay, how to take the, I don't know how to take the image directly, but this one is very good, probability and stochastics. Okay, I don't know. Ernst Sindler. This one is very, very nice. It's a little bit more technical than the things we are doing today because it's more a book for mathematicians. But for engineers, I'm sure there's a lot of things more applied oriented than this one. But this one is very nice. Okay, any question? No, any question? Okay. So if I remember well, there's only one person who doesn't understand French. You don't understand any French, or you can understand a little bit? I think it was Melissa, no?
Any French? Well, I already understand some things, but not this vocabulary.
Okay, because as a tradition, I always like to learn to read. Sorry, the introduction to the book, which is very nice. I mean, it's enlightening, the introduction. So it's I don't know, it's maybe 7 minutes of reading. So is it good for you if I read this in French for the others?
Yeah.
It's just the introduction of the book. Don't worry, you are not losing anything.
Okay.
Okay. So this is the introduction of the book Méthode probabiliste pour l'étude des phénomènes réels, from Bernard Bozami, the second book. And, oui, il y avait une question?
J'ai une petite question avant. Pour les coefficients binomiaux,
Oui.
Pour la démonstration, c'est par récurrence?
Oui, par récurrence, tout à fait.
Parce qu'il y a un problème au niveau de l'initialisation, du coup.
Non, pourquoi?
Parce que si on initialise à 0, A plus
Oui.
P plus 0, ça va nous faire 1.
Oui.
Pour la somme de K égale 0 à 0, c'est nul.
C'est pas nul, c'est la valeur en 0.
Ok, d'accord. Bah, la valeur en 0, ça va faire A puissance n alors.
Ça va faire 1.
Ah oui, ça fait 1 aussi, ouais, d'accord.
Ok.
Ok.
Ça marche. Any other question before? No? Ok. Alors, c'est l'introduction. Ça dit comment se ruiner grâce aux statistiques alors qu'on est un industriel sérieux et réputé. Vous êtes un industriel d'un secteur de pointe, par exemple un laboratoire pharmaceutique, ou bien un chimiste, un spécialiste des matériaux modernes, etc. Et vous voulez mettre sur le marché un nouveau produit dont vous attendez beaucoup. Mais, bien entendu, les autorités vous demandent de montrer que votre produit est sans danger. L'action de ce produit dépend d'un nombre élevé de paramètres. Pour un médicament, ce peut être par exemple la dose absorbée, la durée d'administration, les concentrations afférentes aux différents constituants, mais aussi les caractéristiques propres au malade. Son âge, ses antécédents, son sexe, son poids, son rythme cardiaque, etc. Pour un matériau, ce peut être les différents constituants, les procédés de fabrication, etc. Cette multiplicité de paramètres susceptibles d'avoir une influence est très commune. Même pour les matériaux très anciens, bien que le verre ait plus de 2000 ans d'existence, on n'a pas encore exploré qu'une fraction infime de toutes les configurations possibles, nous a dit un jour le directeur de la recherche de Saint-Gobain. Plaçons-nous ici dans le cas d'un médicament susceptible par exemple, de réduire la tension artérielle, un hypotenseur. Nous ne nous occupons pas des effets secondaires et concentrons-nous simplement, c'est bien assez compliqué ainsi, sur l'effet principal. Le médicament doit réduire la tension, mais pas trop. L'autorité sanitaire dit « Nous acceptons que vous mettiez ce médicament sur le marché si vous nous démontrez que, pour 95% de la population, la baisse de tension obtenue ne sera pas excessive. Voici donc une tension seuil, TS, que nous vous communiquons. Nous savons que descendre au-dessus de TS peut être dangereux. Démontrez-nous que, chez 95% des patients au moins, par l'effet de votre médicament, leur tension ne descendra pas au-dessus de TS. Cette requête de l'autorité de santé est tout à fait raisonnable. Il est certain, en effet, que l'action d'une substance sur les êtres humains n'est pas homogène. Et on peut prévoir une fraction qui réagira davantage. On peut même s'étonner que l'autorité ne soit pas plus exigeante. Elle pourrait demander qu'on caractérise la population hyperréactive, par exemple les personnes ayant des antécédents cardiaques, pour qu'une mise en garde spécifique lui soit adressée. Voyons maintenant comment notre laboratoire va s'y prendre. Disons pour simplifier que l'effet de ce médicament dépend de 30 paramètres. Ces paramètres varient en général continuellement, mais pour simplifier, on décide de ne considérer que des tranches. Pour l'âge, par exemple, au lieu de noter l'âge exact, on considérera des tranches de 0 à 5, de 5 à 10 ans, etc. Ce découpage n'est pas arbitraire, mais ne sera fait scientifiquement. Chaque tranche regroupera 10% de la population. On procède ainsi pour tous les paramètres, et chacun est réduit à 10 valeurs. D'autres paramètres caractérisent le procédé de fabrication ou la composition. Par exemple, le produit est supposé contenir 0,035 mg de cuivre par litre, mais cela peut varier d'un lot à un autre. On modélisera ceci en disant que la composition en cuivre suit une loi de Gauss de moyenne 0,035 et de variance plus ou moins grande selon la qualité de fabrication. Après quoi, comme précédemment, on range le paramètre composition en cuivre en 10 classes d'égale probabilité. Bref, on s'arrange très bien et chacun des 30 paramètres est réduit à 10 valeurs possibles, considérées comme équiprobables. Mais 10 valeurs pour 30 paramètres, cela nous donne 10 puissance 30 possibilités pour les diverses configurations. Et ce que demande l'autorité sanitaire, c'est d'être sûr que pour 95% d'entre elles, soit 95 10 puissance 28, la tension artérielle ne descendra pas au-dessous de TS. Admettons que le test d'une seule configuration demande 1 minute seulement. Cela, évidemment, est absurde. Le test d'un médicament met des jours et des mois. Il faudrait cependant plus de 10 puissance 22 siècles pour tester 95% des configurations. C'est un peu long et les responsables scientifiques du laboratoire ont un moment de panique. Heureusement, il s'agit d'un laboratoire de pointe et il dispose d'une excellente équipe de statisticiens. Le chef de l'équipe, consulté, hausse les épaules et dit « Aucun problème, nous allons vous mettre en place un plan d'expérience. » Il s'agit en l'occurrence de tirer au hasard 10 000 configurations parmi les 10 puissance 30 possibles, en utilisant des lois de probabilité définies sur chacun des paramètres. Par exemple, il y aura tant de personnes entre 25 et 30 ans, tant dont les poids est entre 80 et 90, tant qui prendront le produit pendant 2 jours, etc. Ce plan d'expérience, dûment défini et validé par l'équipe de statisticiens, est mis en œuvre par tout le laboratoire, ses filiales, ses sous-traitants, et miracle, 3 mois après, travaillant jour et nuit, les 10 000 cobayes désignés sont traités et aucun d'entre eux ne présente une pression sanguine inférieure à TS. Tout ceci est consigné, répertorié, analysé et les résultats sont transmis à l'autorité de santé, avec une analyse mathématique rédigée comme suit. Prenons le quantile à 0,1% de la population chez qui, après usage du médicament, la pression sanguine est la plus basse, le millième le plus réactif. Ce quantile est évidemment inconnu. On ne sait pas qui est dedans. Notons le B pour bas. Quelle est la probabilité qu'aucun de mes 10 000 cobayes ne soit dans B? Si les choix sont indépendants, cela signifie que tous sont dans le complémentaire. Et donc la probabilité est de 0,999 puissance 1000. Cette probabilité est ridiculement faible. Autrement dit, j'ai une probabilité extrêmement forte, 0,499, que l'un en moins de mes cobayes soit dans B. Autrement dit encore, si je prends la plus faible des pressions enregistrées chez mes 10 000 cobayes, je suis quasiment certain, probabilité de 0,89, que 999 pour 1000 de la population aura une pression supérieure à celle-là. Comme sur mon échantillon le plus faible est acceptable, elle l'est a fortiori pour 99 sur 1000 de la population. Les résultats vont, semble-t-il, très au-delà de ce qui était demandé par l'autorité sanitaire. Elle demandait 95%. Elle obtient 999 pour 1000 avec probabilité 0,999. Séduite par tant de sérieux dans le raisonnement, par l'ampleur de l'échantillon, par la qualité du travail réalisé, l'autorité de santé donne son accord pour la mise sur le marché. Un statisticien avait même préconisé l'emploi des méthodes de bootstrap qui permettent de tirer des conclusions à partir d'un échantillon réduit. On retire aléatoirement à l'intérieur de cet échantillon. Le bootstrap représente le nec plus ultra des méthodes statistiques. Mais comme l'échantillon de 10 000 était acquis et suffisant, cette méthode de pointe a été écartée. Une cérémonie est organisée par les dirigeants du labo. Les statisticiens sont publiquement félicités et reçoivent une augmentation. En revanche, on licencie les équipes des biologistes. Pourquoi faudrait-il chercher à comprendre l'action du médicament alors qu'il suffit de faire des tests au hasard? Cette cérémonie marque le point culminant du processus d'étude avant la commercialisation. Souvenez-vous de ces instants heureux et souvenez-vous-en bien, car le moment n'est pas loin où, ruiné, poursuivi par d'innombrables plaignants, couvert d'opprobre sur 3 continents, fustigé par les ONG, lâché par les autorités sanitaires, le laboratoire si prestigieux aura disparu, rejoignant ainsi dans la honte les fabricants de Distilbène et thalidomide. Tout d'abord, un vieil ingénieur fait observer que l'on n'a expérimenté que 10 000 configurations sur 10 puissance 30, soit 1 sur 10 puissance 26, ce qui est infime. Mais les statisticiens haussent les épaules, qu'ils ont larges et robustes, et expliquent avec commisération que ces 10 000 permettent de traiter 999 pour 1000 de la population, avec probabilité 0,89. Comme le vieil ingénieur ne comprend pas bien ce que signifie 999 pour 1000 de la population avec probabilité 0,99, il se tait et se résigne. Les temps changent. Un autre, ayant regardé le plan d'expérience, fait observer que n'y figure aucune grande-mère obèse originaire du Tadjikistan. On a bien des grands-mères, des obèses, des Tadjikistanais, on a même une grande-mère obèse et un Tadjikistanais grand-père. Mais on n'a pas de grande-mère qui soit à la fois tadjikistanaise et obèse. Les statisticiens haussent à nouveau les épaules et font observer que les Tadjikistanais sont un peuple vigoureux et que les grandes-mères obèses ne représentent chez eux que 1 sur 1 million de la population. La commercialisation commence. Au début, les choses marchent à merveille. Le médicament est efficace et se vend bien. Il y a certes quelques décès, mais c'est une chose tout à fait normale pour un médicament quel qu'il soit, puisqu'il contient un principe actif. Les décès sont moins nombreux qu'avec les autres médicaments et concernent essentiellement quelques bourgeois obèses ou bien des chefs d'entreprise stressés. Rien qui puisse émouvoir. De plus, il reste un nombre très limité, moins de 1% des cas les plus sévères, confortant ainsi les analyses des statisticiens. Comme en outre le médicament agit efficacement sur le plus grand nombre des gens, les ventes décollent. Le laboratoire s'enhardit et commence à vendre à l'étranger. Par le biais de sa succursale au Groenland, il assure la distribution auprès des pharmaciens et les Esquimaux achètent le produit. Et là, catastrophe. Coup sur coup, 4 Inuits, dont un handicapé, meurent après absorption du médicament. Scandale international, article incendiaire dans la presse, interview du Monde savant, etc. Tout y passe. Qu'une centaine de chefs d'entreprise parisiens meurent en se soignant, cela n'a rien d'étrange, c'est même dans la logique des choses. La nature les punit de s'être écartés des préceptes d'une vie saine. Mais qu'un Inuit, on ne peut plus proche de la nature, vivant de chasse et de pêche, puisse mourir en se soignant, c'est complètement inadmissible. Cela a des relents de néocolonialisme. Si de plus, il s'agit d'un handicapé, on a la preuve absolue de la vulnérabilité des populations les plus démunies face aux offensives bassement matérialistes des multinationales. Que s'est-il passé? Les Inuits consomment de la graisse de phoque, et cette graisse rend le médicament encore plus efficace, faisant ainsi descendre la pression sanguine au-dessous du seuil fatidique TS. On avait oublié de tester la compatibilité à la graisse de phoque dans le plan d'expérience, mais on ne peut pas penser à tout. La graisse de phoque. Le laboratoire contre-attaque. Il explique que les origines du problème sont maintenant connues et qu'il va commercialiser une version particulière du produit destinée précisément aux populations à phoque. Il indemnise largement les victimes et ajoute que les décès ne sont pas forcément imputables aux médicaments. Au moment du drame, les victimes regardaient une série américaine à la télévision et cela a pu contribuer à leur baisse de tension. Le laboratoire crée en outre une exposition itinérante d'art inuit, lequel vaut le détour, comme chacun sait, en fait entrer un Inuit dans l'une de ses conseils d'administration auprès des autorités sanitaires. Le laboratoire plaide que, malgré ces accidents fâcheux, les critères fixés ont été respectés. La proportion des décès est très inférieure aux 5% qui avaient été requis. Bref, comme d'habitude, tout finit par s'arranger. Les Inuits ont leurs médicaments spécifiques, les ventes reprennent et l'optimisme revient. L'Europe est conquise, puis l'Amérique du Nord, l'Amérique du Sud, la Russie, l'Afrique du Nord, tout semble aller pour le mieux. Les ventes sont planétaires. Il y a même des ruptures de stock, parce que le modèle de prévision de vente avait été un peu bâclé. La commercialisation atteint l'Afrique subsaharienne, les Indes, le tour de l'océan Indien, la Chine, l'Australie. Et là, les ennuis commencent. Plusieurs décès suspects. puis en plus grand nombre, des plantes, des associations, des victimes, des explications embarrassées, jusqu'au retrait du produit et au dépôt du bilan final. En très peu de temps, vu l'ampleur de la crise et du scandale. Nous ne nous attardons pas sur ces moments douloureux. Que s'est-il passé? Le médicament contient un principe actif, une huile extraite d'une plante tropicale, le Poinsettia madagascariensis. Le laboratoire est sérieux et, bien sûr, ce principe actif a été testé du point de vue de sa réactivité sur toute une population test. Et cette réactivité a été représentée par une loi uniforme entre 0 et 100. On a trouvé que certaines populations étaient plus réactives que d'autres. On n'en savait trop rien. On a mesuré le maximum et le minimum et, faute d'informations précises, on a conclu à une loi uniforme entre les deux. C'est le choix naturel des statisticiens quand ils ne savent pas. Cela arrive à tout le monde de ne pas savoir. Oui, mais voilà. Il apparaît que les populations du pourtour de l'océan Indien ont une réactivité particulière à cette huile, supérieure à 80 sur cette échelle. De ce fait, le produit est beaucoup plus actif chez elles, et les accidents se sont multipliés bien au-delà des chiffres statistiquement acceptables. Que conclure avec cette fable? Qu'il faut supprimer les statisticiens? Certainement pas. Les statistiques sont utiles et nous-mêmes en faisons. Mais comme tout outil, elles ont un domaine de validité limité. En sortir est dangereux. Nous verrons avec précision dans ce livre quel est ce domaine de validité. Il concerne essentiellement l'exploitation de longues séries de données recueillies par des observations indépendantes. Le mot « longue » et « indépendante » sont essentiels. Si les séries ne sont pas longues et si les observations ne sont pas indépendantes, on peut tout de même construire et exploiter des lois probabilistes. Nous verrons comment procéder. Les probabilités sont une science exacte où le hasard n'intervient pas. On peut construire des lois de probabilité conditionnelles relatives à des situations spécifiques. On ne peut pas extrapoler des statistiques de l'Europe à l'océan Indien, mais le plus grand péché commis par ce laboratoire, celui pour lequel il a finalement été puni, est d'avoir voulu se dispenser de connaissances, d'avoir cru que le hasard pouvait s'y substituer. Il n'était pas utile, croyait-il, d'essayer d'analyser et de comprendre les différentes configurations. Il suffisait de tirer au hasard des échantillons. Le hasard, en quelque sorte, ferait bien les choses. Mais le hasard ne les a pas faites de la même manière pour l'Europe et l'océan Indien. Et ce qui a bien marché ici a échoué ailleurs. La moyenne faite, inconsidérément, ne distinguait pas suffisamment les cas particuliers. L'erreur majeure qui était commise est d'avoir voulu fixer les lois de probabilité initiales de manière empirique. Que ces lois soient fausses, comme c'était le cas, et c'est tout le résultat qui s'effondre. Autrement dit, le résultat 999 pour 1000 de la population avec probabilité 0,99 signifie en réalité, avec une probabilité de 0,99 relative à un ensemble qui ignore 3 milliards d'êtres humains, simple oubli. Si l'on cherche à étudier un processus dépendant de 30 paramètres, les statistiques sont peu d'utilité. Il faut réduire l'espace des paramètres, comprendre que le 13e intervient très peu, que le 18e exerce une influence dans le sens croissant, le 22e dans le sens décroissant, etc. Toutes choses qui n'apparaissent que lorsque l'on comprend comment les médicaments fonctionnent. En d'autres termes, le laboratoire avait besoin de biologistes plus que des statisticiens. Il est en général facile d'éliminer un certain nombre de paramètres et cela réduit la combinatoire d'autant. Pour d'autres paramètres, on réduit leur champ de variation. Au lieu d'un intervalle large, on se ramène à un intervalle plus petit, parce que les valeurs extrêmes, pour telle ou telle raison, peuvent être éliminées. Mais revenons à la question posée par l'autorité sanitaire. Démontrez-nous que, dans 95% des cas, votre produit est sans danger. Nous nous apercevons maintenant qu'elle n'est pas claire. Que signifie-t-elle que 95% des malades doivent ressortir indemnes? Signifie-t-elle que 95% des configurations des paramètres sont sans danger? La seconde est plus générale que la première, car lorsqu'on fait varier les paramètres, on y inclut, comme expliqué au début, toutes les variabilités de poids, de taille, etc. liées au patient. Mais on y inclut aussi les variabilités de composition et de fabrication. Il y a plusieurs versions de la question, et il serait bon, en pareil cas, de demander des précisions à l'autorité sanitaire, étant bien entendu qu'en cas de difficulté, elle rejettera immédiatement la responsabilité sur l'industriel. Mais que la question porte sur 95% des malades ou 95% des configurations, le laboratoire n'y avait pas répondu. Et l'assertion bizarre 999 pour 1000 de la population avec probabilité 0,99 n'a en définitive aucun sens prédictif. Elle ne répond pas à la question posée. Si l'on vous dit, à l'issue du traitement, 95% des malades doivent avoir une tension supérieure à TS, cela a un sens. Vous comptez les malades au quotidien et vous voyez à la fin de l'année combien ont une tension convenable. Mais si l'on vous dit, cela doit se produire avec probabilité 0,99, cela risque tout de même de ne pas se produire. Et sur quoi porte cette probabilité? Qui l'a introduite? De quel droit? Voilà, ce livre répond précisément à ces questions, ok, etc., etc. Donc voilà, c'est un peu l'introduction. Any questions? Des questions? Des commentaires?
Can we have the title and the author of the book, please?
Yes, it's Bernard Bozami. Is this guy?
It's this one.
Yeah, méthode probabiliste
Okay.
pour l'étude des phénomènes réels.
Okay.
Any other question? Or comment? No? Okay. Okay. We can continue with the geometric probability distribution. We are supposed to finish at, we still have 15 minutes, okay? Maybe I can start with the geometric distribution. Yeah, that should be fine. Okay, now the geometric distribution. Geometric distribution. Okay. So a geometric random variable of parameter p, okay, we say that x follows the geometric distribution of parameter p if, okay, so I give the law, the probability that x takes the value k is equals to p times 1 minus p power k minus 1, and this is defined for any k bigger than 1. Okay. You can use g of p or g of p, whatever it is the same. Okay. Anyone can tell me what's the phenomenological description of this geometric random variable?
It's to have, it's for example, if you flip a coin, it's to have, it's the count to have a certain result in a it's repeating a Bernoulli law to the point you have a certain result. Like you flip a coin n times to have a tail.
Yes. Yes, exactly. Okay. So you're launching a number of times the coin. Okay. And you write the result, for example, 0, 0, 0, 1. Okay, so this is the first time 1 appears, and that's for n equals 4. Okay. Sorry, for k equals 4. k equals 4. Okay. Let me just check something. I received an email. Okay. Yeah, so the geometric distribution is the probabilistic law that tells you how it behaves the first moment when 1 appears. Okay. And it follows this distribution. Okay. Probability of x equals k is simply k times 1 minus p power k. Okay. And you can see the graph as before. Before we saw the binomial distribution. Now I can make the same thing, but with the geometric distribution. Oops, geometric distribution, parameter p. Okay. K, p of x equals k. I do not need this anymore. What? Yeah. Oh, yeah, sure. 50. Okay, so it's related actually to a sort of exponential function here, you know, and depending on the value of p, maybe I can fix the range, plot range from 0 to 1. If p increases, then the speed of the function here is bigger, okay? And if p is lower, then the speed of the function is smaller. Okay, so this is how the parameter p affects the PDF, the probability distribution function. Okay. Do you remember we saw this probability distribution function in the first or second lecture? I don't remember. Is the pi function, pi of x. Okay. Any question? Okay. Perfect. Yeah, so that's the geometric distribution. It's the first moment when I have 1. Okay, for example, here, okay, how do you interpret this thing? If p equals 1/2, okay, that means that the probability that the first moment I get 1 when I flip my coin, well, it's slower. It's much more likely to have 1 at the beginning for the first time than after 10 plays or even 100 plays. Does it make sense for you? Normally it's super easy. Okay.
Yes.
Okay, perfect. What can be said about the geometric distribution? Well, the same as before. What's the value of the expectation? Okay, so if x follows a geometric law of parameter p, then the expectation of x will be given by 1/p. Okay, and the variance of x, sigma square x, is simply 1 minus p over p square. Okay, 1 minus p over p square. And yeah, so there's a lot of basic laws you have to know. You have to know, of course, Bernoulli, the binomial law, the the geometric law, the uniform, the Poisson law, and you have other ones like hypergeometric, and then we will start studying the continuous law like exponential, normal, Cauchy, the chi-square, beta, gamma, etc. Okay, and see what are the differences, when they are useful, and how they are related to machine learning. Because remember, the things we are doing here is because we are interested in machine learning, okay? And in some chapters of the next course, okay, so next semester, we will use a lot of Bayesian statistics and Bayesian probabilities and that kind of things, okay? Okay, I think I'm going to start here. Any other question before we left?
Well, I want to know if you can send us your papers, like your notes.
That's a very good idea. Actually, I can. Unfortunately, I don't have the other ones, but this one.
Like the previous courses, you don't have them?
No.
Okay.
I'm really sorry, but it's a good. Yeah, actually, I don't know why I didn't think before.
Like, can I ask now for the next ones? That
yeah,
we can have
please, Alban, remind me every time because my memory is very bad.
Okay, thank you very much.
Data engineering.pdf. Save as PDF on the desktop. Okay, 22 pages. And normally, I don't remember if we have a Teams group. Do we have a Teams?
Yeah, well.
And where? Okay, Energy Lab, it's not that thing. Recherche, 4 APP. Promotion. Yeah, basics of probability and statistics. Perfect. Okay. Please like my comment if you see it on Teams. Hello. If you like, sorry, if you see the comment on the group. Okay, I see one. That's Alban. Okay. I am posting that here. Okay. Okay, so charger, fichier.
If I understand, I'm going to share it with the others.
Perfect. That's perfect. Lecture DE, ça va être ça. Oups. Je l'ai fait ou pas? Sorry, I think I made a mistake. So, quick access and lecture DE. What's that? Open. Yeah, it's there. Okay.
Yeah, it is. Thank you very much.
Yep. Okay. Any other question?
Yes, I have a question. You were saying we will be doing some exercises. I was wondering when it was, because I couldn't see it on my agenda. So.
Sorry, I was reading something else. Can you repeat, please?
Yeah, you said we were going to do some exercises like TP, like in third and second year, and I was wondering when, because I don't see it on my schedule.
I mean TP. You mean to be at school?
At school, I don't know, but like like some exercises we could do, that sort of thing.
Donc ta question c'est, je ne le vois pas sur l'emploi du temps, c'est ça?
Ouais, ma question c'est, est-ce qu'on aurait des TP, genre avec une fiche de TP ou un truc comme ça, un truc pour s'entraîner quoi?
Oui. Et
okay,
quand est-ce que ça va être? En fait, ça va être pendant ma
pendant les
lecture.
CM?
Oui, c'est pendant.
Ah oui, d'accord.
In fact,
okay.
In fact, the lectures and the labs are mixed. So we make a lab when I think it's good. We make a lab during the lecture, and it's a lecture when it's a lecture. Okay. So don't worry, it's at the same time as I am here. Okay.
Yeah, no, I just didn't get it. Okay, thank you.
Okay, if you want, maybe we can do a lab for the next time. Okay, let me check the program because maybe
Sure.
I cannot yet. We're in the description. Okay, so okay, next lecture we are going to do a lab. Okay, I have to prepare the activities. Do
Yes.
you have all Python in your computer? Is anyone who does not have
I think yes, because it's something that's necessary for programming, continuous programming.
Okay, perfect. Okay, so I will assume you all have Python. Good. Well, have a nice afternoon and see you on next time.
See you, Mario.
Thank you. Bye.
Bye.
Bye-bye.
Bye.